All right, our next talk is going to be by Mithat Ünsal, who's going to tell us about fractionalization of flux tubes and screening by emergent electric charges.
Thank you for the invitation. I just wrote this talk yesterday, and I didn't check it. There may be typos in it. Okay, so this is concerning dynamics of confining gauge theories in 3 dimensions, and some curiosity that I had about 2-dimensional setups. In particular, I want to mention this curiosity second step here. Which one is the pointer here?
I couldn't find it.
Okay, good. Okay. So, for example, in QCD adjoint in 2 dimensions, there's an interesting phenomenon, despite the fact that, assuming that this theory has non-invertible symmetry, prohibiting 4 Fermi operators, test charges in all representations, fundamental, symmetric, anti-symmetric, etc., they are all deconfined, despite the fact that the only dynamical field in the system is an adjoint representation. So what screens a fundamental test charge? In other words, let me say it differently, can we have a system in which we do not have dynamical electric charges, but if we put test probes, electric test probes, they can be screened? These two are related questions. And the first one is, so in Polyakov model, as well as in 3-dimensional compact QED, confinement is caused by proliferation of the monopoles. But there are many systems in which it is caused by proliferation of charge n monopoles. Charge 1, you can prove that they are forbidden. And these systems are rather generic. I will give you a list, but first let me remind you a few things about Polyakov model. You can think of it either as U1 lattice gauge theory or SU2 gauge theory with adjoint scalar, where SU2 is broken down to U1. In both cases, if you look to long distance dynamics, it is gapless to all orders in perturbation theory. However, as shown by Polyakov long time ago, there are non-perturbatively monopole configurations. These are instantons in 3D, events in space-time, and their proliferation generate a mass gap. So you can actually map this system to a Coulomb gas of magnetically charged monopoles, and you can write this dual Lagrangian. This is the Maxwell term. This is the term that comes from dual of the Maxwell term. And this is the term that comes from proliferation of the monopole. So, and if you put test charges here, plus minus 1, the spreading of the electric flux throughout the space is energetically very costly. It costs as much energy as the area of the system. So energetically, it is much more favorable to pin a flux from plus charge to minus charge. And there is a flux tube between these two, electric flux tube. Okay? This said, there are many systems in which, okay, let me go back forward. Confinement is caused by this kind of operator, cosine and sigma. Okay, now let me move back. And let me tell you a few places where this occurs. For example, in 2-dimensional quantum anti-ferromagnets on bipartite lattices or honeycomb lattices, you do get that kind of confinement. Sigma is still 2 pi periodic, but you do get cosine 2 sigma, 3 sigma, 4 sigma. It depends on the circumstances. So in SU2 gauge theories, if you have dynamical fermions in adjoint 3-index and 4-index symmetric representation, you can show that the object that generates mass gap for gauge fluctuations have magnetic charge 2, 5, and 10. Okay, it's a very weird object, cosine 5 sigma. Okay. De Formia and Mio set theta equal pi. it generates cosine 2 sigma. Monopole is forbidden. Quantum diamond model. And if you are doing lattice U1 lattice gauge theory, and if you restrict monopole sums, you can generate anything you want. So the mechanisms through which these cosine and sigma type monopole cluster potential is generated, the mechanism by which these things happen are different. The first one and the third one are intimately related. The first one and the third one are, you can show that monopoles have some, you have two identical monopoles, let's say here and there, but they have, for example, one of them has Berry phase trivial, the other has Berry phase pi. So they can destructively interfere with each other and kill each other's effects. This thing happens either via Berry phase, topological theta angle, or in the case of U1 lattice gauge theory, the phase implementing monopole charge constraint. These are the same thing, essentially. If you have theories with fermions, then index theorem tells you a given fermion will have certain number of Fermi zero modes. Hence, it will be impossible for that monopole to generate a mass gap, but certain clusters of them will do. These are called magnetic baryon and higher clusters. Okay, so I put a picture here. This is what happens in QCD adjoint on R3 cross S1. You have monopoles plus minus. These are BPS and KK monopoles. They have lots of these. They have two Fermi zero modes each. This is number of flavor being one. But there are also these clusters plus. They have a characteristic size you can calculate. It is larger, much larger than monopole size. So these things have magnetic charge too, but no Fermi zero modes, so they can generate confinements. If you are doing U1 lattice gauge theory, you can achieve confinement via any charge n. The idea is following. Starts with the Villain form. This is called Villain action. And it has the usual confinement a la Polyakov. Then you can insert these phase factors. QZ is the flux associated cell with some cube here. And if you sum up over this KZ, you can, and depending on your choice of n, you can forbid all the monopoles. All the monopoles will have a cancellation between them, but the monopoles that will not cancel are the clusters with cosine and sigma. Depending on how you put this, you can put it on a single cube, or you can insert this sum over a very large cube. As a result, the constraints will be different. The only thing that will differ is the fugacity of these monopoles. Here, this is technical, it's not that important. Now, the question is following. Let's say we have a confinement via this. What changes? So first of all, if you look at the system, obviously, sigma is identified with sigma plus 2 pi, and it has n isolated vacua located at these points. And there are domain walls between them. These are domain lines in two spatial dimension. And if you assume one of them is in x1 direction, you can find its profile in the x2 direction by minimizing this, extremizing this energy functional. The solution of this is just instanton equation in one dimension with these boundary conditions, and there is a fundamental string tension. And now, if n was 1, as I said, there is a minimal electric flux tube forming between them, and the thickness of this thing is given by the Debye length. This flux tube is also solution of the instanton equation. These are same equations, but now with different boundary condition. Sigma at minus infinity is 0, sigma at infinity is 2 pi, so you have to pick up this 2 pi monodromy going around this charge. So this is for charge 1. What happens for charge n? What happens to this flux tube? This is the question. And here is the answer for n equal 3. Okay, so if you go ahead and look for the minimal energy configuration, you can show that the flux emanating from this one, there is still linear confinement, but flux splits to 3 for n equal 3, in general to n. And each one of these things is carry an electric flux, which is 1 over n, 1/3 in this case, and there are 3 of them. But the interesting thing is, the thing that you thought was the flux tube is actually a combination of the domain lines of spontaneously broken Z-n symmetry. This is domain line interpolating between vacuum 1 and vacuum 2, and domain line vacuum 2 and vacuum 3, so on and so forth. So the flux tube, fractionates into n domain lines, each of which carry fractional electric flux equal to 1 over n. This is not the first observation of this. The first observation of this is due to a nice paper by Anber, Süleyman Pasic, and Popitz. They show that in the case of n equal 2, instead of having one flux tube, you do get a pair of flux tube, each of which carry 1/2 electric flux. And they also showed something very interesting. If these things carry 1/2 electric flux, you can actually put a charge -1 and charge 1 quarks here. And as you can see, all it does is flip the orientation of the flux. These things will be liberated on this domain line. This is actually dimensional reduction of a very nice effect discovered by Soo-Joon Ray and Witten. What they observed is that in softly broken n equal 2 theory in 4 dimensions, if you consider a domain wall interpolating between monopole vacuum and ion vacuum, electrically charged quarks are actually free on the wall. They are confined in the bulk, but liberated on the wall. This is a field theory realization of that idea. Now, this is my setup. This is fractionalization of the electric flux tube. Now, I will talk about what happens to this setup when you do compactification. When you do thermal compactification, it is more or less obvious, well-known story. These monopoles in 2 dimension goes to global vortices, and they have BKT type phase transition. And in my system, I do not want phase transition. I want adiabatic continuity as much as possible on R2 times S1. It tells me to do a twisted compactification. For the dual photon, I will employ this boundary condition, which is twisted by charge conjugation. What happens when you do that? For example, let's take n equal 4. N equal 4, the flux splits to 4 fractional flux, and they can go from +1 to -1. But twisted boundary condition tells you that in the next slice here, there is a minus. Go ahead. You can go either this way, but now flux can start here and end up there too. That's also a possible configuration. Or what you can do is, this is compactification scheme. It can start here and it can split to 2 flux line going up, 2 flux line going down. And this is consistent with Gauss's law and everything. And you can achieve something like this. This is very interesting because now I can take these things apart and it doesn't cost any energy. You show that when you compactify this theory, there will be a term proportional to area law, but there will also a term proportional to perimeter law. Interesting. Now let us do the same exercise for n equal 5. Now, 5 fractional flux lines. Ultimately, what can happen is 2 can go up, 2 can go down, and 1 goes this way. Each one of them carries 1/5. So it is consistent with Gauss's law and everything. But here, area law did not turn to perimeter law. Area law turned to another area law, but the string tension diminished dramatically. If you look to expectation value of the Wilson loop, you can write it in this way. Energy of these configurations, you can write them. There's a part proportional to the separation between them, and there's a part which is proportional to the length of the compactified direction. This is energy of some configuration there. But the main point is you can write the expectation value of the Wilson loop in this form, an area low term, perimeter low term. If R is less than L2, you have a tension which is large. For an odd R is greater than L2, you have a tension which is sigma naught. And if n is even, it is 0. Okay, so this is the plot, and this is the effect that we observe. So string tension diminishes here, and it has some non-zero value there. Now, I want to explain this phenomena from a different perspective. What I want to do now is, instead of using twisted boundary condition by a field definition, I want to turn twisted boundary condition to periodic boundary condition, but I keep the effect on the field. So this comes out to be equivalent to insertion of some topological defect lines. These are defect lines in space, but if you think space-time, these are really surfaces. At some position x star, arbitrary position x star on S1. So this is the picture. There is a defect line you put somewhere. What happens is that traversing this defect line, the state flips according to some rule, and the domain lines flip according to some other rule. And now, okay, let me go back. The junction of this defect line and these domain lines must absorb the flux. For example, here the flux is 1/4 coming from there, 1/4 from there. So this thing must carry, this junction must carry an electric charge, fractional electric charge, -2/4, and this one +2/4, -2/5 +2/5, so on and so forth. So these junctions must support some amount of. Do I have 10 minutes?
Yeah.
Oh, that's wonderful. Huh. Okay, I can even slow down. So really, okay. These junctions support these fractional electric flux. As a result, for example, if you look to the picture for even n, this is n equal 4, you can have a picture like this, +1 here, its flux is going out, and remember, now I have periodic boundary condition. You see, if flux is going this way here, it must go this way there. It is different from this previous picture. You see, these things were opposite to each other.
I have a question. You have those configurations. A trivial question. You have those configurations with the set lines, the particles are like a ladder mass now. That energy contributes to the mass of the particle.
Say that again.
You have these particles that have the line to some mirror of
Oh, yeah.
So now the particles have more mass there.
You can ignore it because you can take this compactification scale very large. It doesn't matter. The interesting thing, you can ignore that for sure. The interesting thing here is that, one can think that, oh, I'm sorry. One can think that this is like a genuine phase transition kind of thing with compactification. But this is a relatively strange phenomenon. The scale at which this happens, you compactify to a circle. It may be very large. And you look at Wilson loop. If Wilson loop is smaller than that very large thing, it will be linear confinement. If the Wilson loops get larger, it will go to perimeter law. So this is happening at very large scale. Because of that, when you do this method of images here, you know, it shouldn't be too much hassle. It shouldn't cause any problem. Yeah. So all of these phenomena can be at very large compactification radius. It's really an interplay between size of the Wilson loop and size of the compactification. And compactification size can be arbitrarily large here. It doesn't need to be small. Okay. So here, for example, +1 can be screened by its flux can be absorbed by these -2/4. The combination makes -1, so the whole electric flux can be eaten by this. There is something very curious. The electric flux lines, the strings, are always present, right? It is funny, and yet you are going from a picture where you have an area law to a picture where you have a perimeter law. But confining string is always present regardless. It's very strange, but they are not always present in between these two. You know, they are present in one way or another, but they do this thing. To me, this is the very interesting thing about this is following. So in the models I started, for example, U1 lattice gauge theory, where I restricted the monopole sum, there are no electric charges. There are no dynamical electric charges. Even when you compactify the theory, there are no dynamical electric charges. Okay, and yet we observe these fascinating phenomena of screening of the electric charge. Actually, I came this question in a paper in 2D QCD adjoints. Unlike QCD adjoint on 4 dimension on R3 cross S1, 2D QCD adjoint was always very difficult for me to understand. It is very mysterious theory. And one of the very mysterious things about it is the thing I said at the very beginning. How on earth a fundamental charge can be screened, you know, in a theory in which dynamical matter is only adjoint? And this was a question I saw in a paper by Igor and David. I thought it was a very interesting question, and I thought maybe it shouldn't. Well, maybe it does. Yeah. This is what happens here in the setup. So these junctions carry emergent fractional charge, and they can indeed cause either perimeter law or, you know, change the string tension dramatically. Now, this thing will be related to Martin's question, but from a different perspective. Now, if you were to have monopoles on R3 and compactify it on a thermal circle, these monopole operators, if you look up them in 2 dimensions, they will go to global vortices. And for the global vortices, you will have a BKT transition. And there will be, when you do that compactification, you are destined to have a phase transition. This is something well studied. But as I said, I did a compactification by using this twisted boundary condition by charge conjugation. Okay? Now, what I did is I perturbatively gapped out the dual photon. I gave it a perturbative mass, which is 2 pi over 2L. Now, then monopoles, you know, the interaction between monopoles will no longer be long range. So this twisted boundary condition will turn the monopoles to local vortices. And so what happens if we look to long distance 2-dimensional theory? What happens? You know, first let me put a reminder if you have a Wilson loop and if you have a monopole, what Wilson loop measures is essentially this solid angle for one monopole. And the proliferation of this, if you have many monopoles in the bulk, this is the thing that generates area law. If you have vortices into the, however, the relation to Wilson loop is, you know, if they are inside, they give you non-trivial phase. If they are outside, they do nothing. Now, what happens with this twisted boundary condition with monopoles? You put a plus charge here, but the image will be minus, and you will continue this at infinitum. So this problem actually maps to a very simple problem that we study in electrostatics. You know, the field of the Coulomb field of a charge in the presence of two conducting plates. And it's a whole section 17 of Schwinger's book is devoted to this. Something very interesting happens. You have these alternating array of charges. You sum them up. All of them have fall-off, which is 1 over r, algebraic decay. But if you sum them up, they decay exponentially. So the field is gapped out, that's to say. So what happens to flux? When this happens, half of the, now I am talking about magnetic flux. Half of the magnetic flux goes up instead of distributing spherically symmetrically, half of it goes down. What does this imply for the Wilson loop? So for the Wilson loop, if you are looking, R is much less than L2, it is still the same relation between monopole and Wilson loop, this solid angle. But if you are looking, let's take, for example, Wilson loop with charge n. If you are looking to very large Wilson loop, then this theta here is integer 1. So what happens is that for odd n, this phase factor becomes exponential I pi, non-trivial. But for even n, the phase factor here becomes 2 pi, multiple of 2 pi. So for odd n, you still get an area law at large distances, but for even n, you get perimeter law. Okay. Last slide. So I think it would be interesting to derive the string dynamics for these confining gauge theories. There is a nice paper by Polyakov, maybe 20 years ago or something like that, in which he does that in U1 gauge theory. But I am not sure of the details. I am pretty sure it's correct. But in particular, in certain cases, we have, by tuning certain continuous parameters, for example, in the Fermi-Mills, by tuning theta angle, you can go from a monopole-induced confinement to magnetic bion-induced confinement. And throughout this process, the string between these external probes must fractionate. I think it would be very interesting to see this visually or analytically. That's all I want to say. Thank you.
Yep. So I think we lost track of part of the picture. So in the 3D models we were studying, what is the fate of the one-form symmetry on R3? Is it preserved or not?
On R3, it is preserved. There is always confinement.
Good. That's what I thought. Now imagine we take the opposite limit. We go to the R2 limit. Then it's spontaneously broken.
In some cases, it is spontaneously broken. Yeah. On R2, one-form symmetry on R2 for an even is spontaneously broken. But this is not a usual phase transition. You know, it is not associated with the physical scale in the problem. It depends on it doesn't matter what the size of the circle is. As long as you make your Wilson loop large enough, you will see broken for an even.
Yeah, I understand that, but then my next question is like, do you have some understanding of how the spontaneous symmetry breaking in the 2D limit
is consistent with the Coleman-Ragnar theorem for one. It should not be, naive, it shouldn't be possible, but maybe it can be, there's a right Bolt anomaly, but I didn't expect this kind of anomaly here.
Yeah.
How do I think about
Okay, generically, one form symmetry should not be broken unless there is a reason. I bet in each case, I put on the third slide also, the story will differ subtly, in a subtle way. But I can answer, for example, for the fermion meals. Let's say you started with the fermion meals on R3 times S1. You have either at theta equal pi, it's Bion-induced mechanism. But if you go to R2 limit with this twisted boundary condition, as a manifestation of the anomaly, exactly as you say, mixed anomaly, the one form symmetry must be broken. So in each case, there will be subtle reasons like that. But I cannot answer all of them at once because, you know, the dynamics of each theory is different. But if you are asking in the context of pure U1 lattice gauge theory, precisely, it's a more interesting question.
let's talk later. It's
Yeah.
It's non-trivial.
Yeah, that's a more interesting question.
Yeah, so I propose that we continue this discussion during the coffee break, which will be in the same room where you had breakfast. Please remember to send your slides in PDF form to Yuan. And now let's spend meet up more time.